Now, all of our transformations we had to do with all of our new exponential graphs. You're going to have to do all of your transformations with all of your log graphs as well. So you're going to need to be able to quickly draw a log graph of any base. Now, if you can graph the exponential graph that goes with this, you can graph its inverse, because all you have to do is switch x and y. So at the beginning right now, what I'll get you to do is I'll get you to think of your exponential graph, y equals 4 to the x. You know it has an asymptote at y equals 0. You know that it goes through the point 0, 1 and 1, 4. Then your log graph, all you're going to do is switch x and y of those points. So if every exponential graph, remember that every exponential graph has 0, 1. What does that mean? That every log graph is going to have 1, 0. And if every exponential graph has 1, whatever the base is, because when you plug in 1 you get 4, that means every log graph is going to have the base, 1. And the shape of a log graph looks like that. And since our exponential graph had y equals 0, if you switch x and y, that equation becomes x equals 0. And so we have an asymptote at x equals 0. So now that we've graphed our log graph, we can answer any intercepts. Well, it has an x-intercept at 1. It has no y-intercepts. The equation of the asymptote is x equals 0. And finally, if we are figuring out our domain and our range, well, the domain of your exponential is everything. That means your range of your logarithm is everything. The range of our exponential is y is greater than 0. Oops. That means the domain of your log function is x is greater than 0. Questions you can do for graphing are 10 and 11. And what I'm going to get you guys to do now is just at the bottom of page 378. Bottom of page 378. I'm going to introduce you to the natural log of x. Because right under the log button on your calculator is a button that's ln. That stands for the natural logarithm. It's French, so they put logarithm naturel or something like that. That's why it's not NL. So the natural logarithm is the logarithm that happens. Ln x is the same as log base e of x. So we can have all sorts of different bases, but the natural log happens so often that instead of having to write log base e of x all the time, it's got its own special function. And look how much time that saves you. You have to write 2 less letters every single time you want to write it. So it's a huge time saver. So if we think of log base e of x, if we were graphing this logarithm, and what I want you to be able to do is go directly to your log graph. So I want you to know what point is on every single log graph. 1, 0. The other point is always the base, comma 1. So this one will have e, which is 2.718, comma 1. And the shape of a log graph is the same with an asymptote. At x equals 0. Was that too quick? No, it's good. So now, if you can graph the parent function of any log graph, then you can do any transformation of any log graph. And it follows the same rules. If something happens where the x is, that's going to move it left and right or make a horizontal stretch or compression. So if I had this, and I'll put brackets around this so that you can see that that plus 2 is after the log 3 of x. What is that going to do to my graph? It's going to move it 2 up. Okay? What's that going to do to our natural log graph, the one that we just graphed? It's going to move it 7 to the right. So here's our graph. If I redrew it right here, it would just move 1, 2, 3, 4, 5, 6, 7 to the right. Instead of 1, 0, you would have 8, 0. Instead of e, 1, you would have e plus 7, 1. And instead of an asymptote at x equals 0, you would have an asymptote at x equals 7. So again, it's really important that you know what the parent graph looks like so that you can do all your transformations. The other thing that's going to become important for you to notice is, what is the parent graph? So here I put a lot of numbers in. What would be the parent graph for this one? The base graph, y equals what? Log base 7 of x. And it's important you know which is the parent graph, because that means that this 7 doesn't affect any transformations, because that's part of our parent graph. And here's our x. So this log base 7 of x, there's our parent graph. So what is the 3 going to do? Multiply the y by 3. What's the 2 going to do? Multiply the x by 1/2. What's the 8 going to do? It's going to move it to the left 4 units. Right? Why does the 8 move it 4 units to the left? Because you have a horizontal stretch with a horizontal translation. So before you would do anything, you would probably rewrite this and factor out that 4. So it would go 4 to the left, and finally the -4 would move it 4 down. So you would take your two key points on your log 7 graph, which every log graph has 1, 0, and a log 7 graph would have 7, 1, and the asymptote x equals 0, and do all those transformations to all those points. You might even draw a quick little sketch of log base 7x first, just to see what it looks like to begin with, and then do those transformations. Y by 3 and x by half. Then x minus 4 and y minus 4. Left 4 and down 4. The only thing that's going to affect a vertical asymptote is when it moves left and right. Well, vertical asymptote starting at 0. Because when you multiply anything that's at 0 by anything, it doesn't change. But when you move it left and right, it will change. So this asymptote, because you're moving 4 to the left, the asymptote's going to end up at x equals minus 4. So that's graphing with logarithms. The same thing that we've graphed with exponentials, the same kind of graphing we've done all along in our transformations. So the nice thing about these units is you get to review transformations while you're doing them. But most of the homework in here is about using your new definition of what a logarithm is, and it's such an important definition that I will give you some time to work on those questions, especially from example 1 and example 2, so you can do that now.